Hello everyone, welcome. This is Tronic Synergy. So we have a very simple project right here where the logic is very simple. We are using a DH11 temperature sensor to check the temperature of the surrounding, and it's directly proportional to the speed of the fan. So if the temperature rises, the speed of the fan also rises. If the temperature drops, the speed of the fan also drops. Now for our circuit, we are using an Arduino Nano as our microcontroller, and we have a very simple circuit here, which is a power supply circuit, because we are powering our circuit from the mains, where our mains is 250 volts, 250 volts, 50 Hz AC. Now we need our circuit to take that and transform it from 250 volt AC into 12 volt constant 12 volt DC for the fan, and also some around 5 volt for the Arduino Nano and our DH11 sensor. So we are going to check into we're going to look deep. We're going to go deep into our calculations to see how that is done. So we're going to start at this point where we know that our loads are the fan is our main load, which takes around 12 volt and 0.12 amps. That's actually recorded on the if you can see, if I can just zoom it, you can see DC 12 volt 0.12 amps. So now that we know that, now our Arduino Nano plus DH11, the Nano takes around 14 milliamps or 0.04 amps, and our DH11 takes around 2 milliamps. Now, if we take these two, it's going to give us approximately around 50 milliamps or 0.05 amps. Now, for safety measures, if we take the fan output, which the fan input, which is around 0.12 amps, and add that of the Arduino Nano plus DH11, which is 0.05, we're going to check it's going to be 0.17. Now, for the safety margin, just to be safe, we're going to add, or we're going to just to round off it to around 0.2 amps, which is being taken by the Arduino Nano and our temperature sensor DH11. Also the fan as our main load. Now that we know that, we're going to go now lower into the power. Now the power is very important, because we are taking from the AC, the red wire, which is bringing in AC. Our transformer steps that AC down to 12 volts, down to 12 volt 1 amp. Now the apparent power will be 12 multiplied by that 1 amp, which will give us around 12 VA. That's the apparent power from the transformer. This is not the real power. There's a difference between apparent power and real power. Now, real power is where you take into consideration if your load is capacitive, inductive, or resistive, things like that, the power dissipation by heat, things like that. So apparent power is just the power which is being taken from the transformer without any, that's just the power output of the transformer under normal conditions. Now we're going to go down to the KBP 307 rectifier, because that's what we are using right here. So this top device right here is the KBP 307 rectifier. It's just a simple bridge rectifier inside, and we need to know what's the peak voltage. Now the 12 volts which are coming from the transformer are that's the VRMS AC. Now we need to know the V peak. Now the V peak will be VRMS multiplied by root 2. Now what you're going to notice is that what is going to come out of the rectifier is actually higher. It's actually at 16.97 volts. Now this is DC. It's from the rectifier, but not constant DC. It's a pulsating DC. You need to take a note at that. There are two different things. So also we need to also consider, we need to also put into mind in that, because it's a bridge rectifier, there are 4 diodes inside, and for every silicon diode under any load, they will have a drop of around 0.7 volt. So we're going to just take it as 1 volt, and because at every given cycle 2 of them are going to be conducting, that means at any given moment it will have a 2 volt drop. So we are going to check our 16.97 V peak minus 2 volt, which will give us around 14.97 volts. 14.97. Now this is what is gotten out of the rectifier right there. Now we're going to go to the smoothing capacitor, which we are using at 330 UF or a microfarad, and it's rated at 25 volts. and we are going to now calculate the ripple voltage. Now the ripple voltage, the voltage, because our circuit is drawing current, is drawing, now the voltage is going to drop. At moment our voltage is going to drop, and that drop is what we call the V ripple, and it's calculated by I load, which we got was around 0.2 amps, and you do divide it by 2, multiplied by frequency, multiplied by the capacitance which you're using, which is 50 hertz, because that's the supply around. Then our capacitor is 3300 UF or microfarad, and that's going to give it a 0.60 volt, 606 volt. Now that's the voltage drop. Now we're going to take that 14.97 and we're going to minus that, and that will be a 14.36 now out of the capacitor. Now we are going into the regulators themselves. Now the regulators, we have chained them in a way, it first passes through the 7812, then goes to the 7805. Now this chain helps us because from the 7812, the 7805 will not have a very huge amount of power or voltage to drop. That helps it to maintain its temperature, because it's quite better to drop around 7 volt other than taking the whole 14.36, and because this is a 5 volt regulator, we're going to be dropping around 9 volts or 10 volts or so. So this is actually better to chain them. Yeah. So from the 7812, we get around we're going to get around the 14. We have already calculated that. Then 7812 drop out voltage is around 1.5 to 2 volts. So the voltage required by the 7812 to actually maintain 12 volt output is going to be around 13.5. Now if you take, for example, if you take this 13.5 and compare it to the 14.36, which is being is at the input of the 7812, it's quite well stable to produce the 7812, because it's lower. This one is lower than what we are giving it, so it's going to work just fine. Yeah. Then the power dissipation now, because a 12 volt regulator, the 14.36 input minus 12, you're going to get that 2.36 is going to be lost as heat. And if you calculate the power, because we need to know the power which is being dissipated. Now power is equals to VI. Then we're going to take the 2.36 multiplied by 0.2, which is going to be 0.47 watts lost as heat. Yeah. Then 7805, the same. So input 12 volt, which is coming from the 12 volt regulator. Then output is around 5 volts. So the drop is 12 minus 5, 7 volts. But the current is actually 0.05, so it's not going to be dissipating a lot of heat. It's going to just dissipate around 0.35 watts, and that's what will be noticed. And this is quite lower. If you notice, I've not connected heat sinks at the two regulators. This is a MOSFET. This one in the middle here is a MOSFET. The two are the regulators. I've not connected a heat sink. I'm still going to look for it. But for around 0.347 and 0.35 drop or power dissipation by heat, it's not quite strong enough to actually do any big damage to our regulators. Yeah, so that's our circuit. Now I'm going to put a soldering iron near our DH11, and we're going to observe the difference. So I'm going to take this here, and it's hot already, so we're going to check if it increases the speed. So let's hear. Now if you hear the sound of the PWM has gone, means that the fan has already increased the speed because of the difference in temperature. Means that the temperature risen, so the fan speed also increased. Yeah, so that's how I'm going. Wanted to show you. I mainly wanted to show you what is really happening in terms of calculations, but this will be quite hard to actually show you. But I can actually feel the difference because right now it's running faster than before. So that's what I want to show you. Yeah, so next time we're going to do also other projects, and I'm going to show you how you do calculate them. Yep.